Hello, today we'll conclude with the origin of hydrocarbon resources, developing an hydrocarbon fluid migration within the underground while introducing the different typologies of our resources. Last time, I introduced the downward part of the story, from surface sediment deposit to the expulsion of hydrocarbon fluids from the source rock. Our objective was to understand how sediment generates hydrocarbon fluids. Today, we will focus on the underground migration of hydrocarbon fluids, these fluids being not so dense as water that they will aim to move upward. Therefore, looking at migration pathways will allow us to understand and inventory the wide spectrum of natural hydrocarbon resources. Our main objective will be to understand the origin of the different typologies of hydrocarbon, which indeed reflects the different underground fluid flow stories. Another objective will be to introduce very basic notions of fluid flows in porous media. For our travel in the underground, we will use this particular schematic geological section to comment on an example of hydrocarbon migration scenarios and to illustrate where the different typologies of hydrocarbon resources can be found. At first, we can consider four main domains: the atmosphere, the sea, the continental basement, and finally the sedimentary rock domain, where hydrocarbons are generated and displaced. If real, such a section would be a testimony of a quite complex and long geological story during which large-scale tectonics and erosion processes strongly reshaped the Earth, tilting formations, faulting them while eroding others and creating new ones in a permanent way during hundreds of millions of years. Faults, depending on their sealing, play an important role in fluid migration, isolating or connecting the different compartments noted here, A, B, C, and D. In our case, we will assume the fault separating compartments A and B to be permeable. Fluids can circulate in the fault, and the two others as impermeable, being sealed by some minerals. Indeed, in each location, it is a particular story geologists will aim to understand when addressing oil and gas production. Let us look in detail at this sedimentary formation composed in our specific case of two source rock, mainly shales, coal, and different types of clays and sandstones. These different kinds of rocks represent more or less porous and permeable materials where hydrocarbon fluids can or cannot displace through or accumulate into. The porosity represents the amount of void in a medium, such as all volumes in a piece of sweet cheese. The permeability reflects the ability of a material to allow fluid to displace through it. It represents the way pores and open fracture networks are connected. Permeability is reported in darcies or more generally in midi-darcies. The more the compaction of the rock, the less the porosity and permeability in it. Let us now focus on the geological sequence in compartment A. The deepest and oldest sedimentary layer, a source rock in brown, is first overlapped by a tight sandstone formation in light yellow. Then a thin coal deposit in black, a second tight sandstone formation, and a second source rock deposit. All these formations correspond to extremely low permeability formations. Fluid migration in such formation is not easy due to capillary pressure effects. Above, two porous and permeable sandstone layers, in yellow and orange respectively, covered by an impermeable clay formation, have been more or less eroded over time from one compartment to the other. Such sandstones are excellent carrier systems for fluid migration, and on the contrary, clay is an efficient barrier such as the source rock themselves. The red line corresponds to the geological erosion limit of this oldest sediment. It is called unconformity and delimits two main geological stages. Note on the left part of the figure all these sediment outcrop. This is very helpful for the study of buried sediments. On the right part of the figure, these sediments remain buried, but they have been uplifted during tectonic phases. This means they were buried deeper at a higher temperature and pressure some millions of years ago, making the maturation of organic matter possible. Back to our geological section now. The recent sedimentary layers correspond to another type of clay in light green and to two very different permeable and porous sandstones. Now, let us consider the different scenarios of migration of the hydrocarbon fluids, taking into account petrophysical rock properties such as porosity and permeability, in situ stresses, pressure gradient, temperature, etc., and source rock maturation. Last time, we saw that hydrocarbon fluids were expelled from the source rock if it was mature enough. Most fluids remain within the source rock. Now, let's start our inventory of the hydrocarbon resources. First, let us consider the hydrocarbon remaining trapped within the source rock, which represent huge resources worldwide. They are nowadays exploited in North America, delivering light oil, condensate or gas, better known as shale oil and shale gas. Oil or gas will penetrate the tight sandstones and will be trapped due to the very low permeability effects. Hydrocarbon resources present in these formations can be disseminated in wide sedimentary areas. They represent huge resources and can be produced in a similar way as source rocks. To be exhaustive, we have also to consider the gas generated from another kind of source rock, the coal beds. Methane is trapped within the coal itself and is produced thanks to the natural fracture system. Hydrocarbons will also easily penetrate high porosity, high permeability sandstone located above, starting their long-term upward migration. At this stage, there are two main scenarios when considering migration. Nothing blocks the migration of hydrocarbon fluids, allowing them to reach the surface. It is blocked or affected by a barrier of permeability, such as a clay formation or a silt fault, which will block them or will affect their pathway. When nothing blocks the migration of hydrocarbon fluids, as in compartment A, they reach the surface as oil and gas seeps. At shallow depths, oil can be biodegraded, creating tar sands and bitumen or extra heavy oil deposits, such as in Canada and Venezuela. In another geological context, such as in compartment D, gas penetrates the shallow porous sediments, and in presence of water, changes into solid hydrates due to specific high pressure and low temperature conditions. Huge amounts of gas are trapped under hydrates in large areas worldwide within Arctic domains and deep offshore. Now, let us consider the case where hydrocarbon fluids migrate into the geological cul-de-sac. No escape is possible, and fluids will accumulate over time in this local and limited trap as indicated here. It is the combination of a porous and permeable rock, which we call a reservoir rock, capped with an impermeable one, a cap rock or sill by definition. The production of hydrocarbon fluids located in structural traps is the most common way to produce oil and gas today. In other words, it is conventional. By comparison, all the other scenarios are called unconventional ones. Our last case corresponds to immature rich organic source rock. This is the case in compartment A for source rock located at shallow depths. Producing oil from such resources is possible ex situ after mining and heating. These huge hydrocarbon resources are known as oil shale resources. This concludes our introduction on the origin of hydrocarbon resources. In the next lectures, you will focus on the exploration and production of conventional hydrocarbon resources. Have a nice trip in this world of technology and challenges. Bye-bye.